So here we are in the amine chapter, the last chapter of work 2. Amines are important because it allows us, using the nitrogen atom, to change a lot of different functional groups around. So we have a lot of functional group transformations we can do as we go through this chapter, so it helps out with that. It helps tie everything together really nicely, but we can have as we talk about amines, we have ammonia, and then we have a primary amine, a secondary amine. Primary amine has one alkyl group on it, a secondary amine has 2 alkyl groups on it, and the tertiary amine has 3 alkyl groups on it. And remember, amines are different than alcohols. In an alcohol, a primary alcohol is talking about what's off the carbon containing the OH, whereas the amine, we're talking about what's off the nitrogen. So the reactivity of amines, an amine can act as a base by adding an acid to it, where it can scavenge a hydrogen off of it to form the ammonium salt. An amine can also act as a nucleophile, and nitrogen is a really good nucleophile. It can attack a carbon with a leaving group on it to form also a quaternary salt. So how do we name amines? We look at what's off of the nitrogen and end with amine. So the first one here is ethylamine, because we have an ethyl group off of the nitrogen. The second one, cyclohexylamine, and the third one, isopropylamine. Okay, that's when we only have one group off of it. If we have multiple groups off of it, we name each one cyclohexyl-ethyl-methylamine, or if they're all the same, triethylamine for that. The geometry of an amine, the nitrogen is sp3 hybridized. We know that from a long time ago. It has 3 bonds and a lone pair around it, and being sp3, it's trigonal pyramidal in shape. So what do we know about amines? Well, they're kind of in between the colligative properties of an alcohol and an alkane. Pardon me. When you talk about the similar molecular weight sizes, an alcohol has a high boiling point, whereas an amine is much lower, but the amine is much higher than just the alkane. So it doesn't hydrogen bond as well as an alcohol, but it still has some to raise the boiling point up. Okay. The more branched it is, the lower the boiling point. So propylamine and propylamine versus ethylmethylamine. The propylamine has a higher boiling point, and we go down to trimethylamine. The boiling point lowers even more. Hey, amines as a whole smell bad, smell poorly. Okay, when you get 2 amines on there, and we have 2 examples down here, putrescine and cadaverine, they smell even worse. So the basicity of amines, triethylamine can act as a base to pull a proton off of a carboxylic acid. So in the mechanism, it goes and grabs the hydrogen, breaks the HO bond to give us the quaternary salt and the carboxylate. We also remember resonance structures. We can send the electrons from the nitrogen into the ring, and we get a negative charge on the orthocarbon. We can send the negative charge to the paracarbon, and then we can send it to the other orthocarbon, and then we can send it back to the nitrogen, resonating it all the way around the ring. Amines at physiological pH, the amino group ends up accepting an extra hydrogen and really exists as an ammonium ion. So how can we prepare amines? We've talked about all of these ways in the past, but we'll talk about them again. We can use the cyanide ion to do an SN2 on a primary halide to make the nitrile, and then we can reduce that with LAH to make a primary amine. We can take a carboxylic acid, make the acid chloride, and then make the amide, and from there we can reduce that amide down to with LAH to the primary amine. So the first way with the nitrile, we added a carbon onto the chain. The second way, starting from the carboxylic acid, we did not add a carbon onto the chain. Okay. We can also make aniline and all its derivatives. Starting from benzene, we can nitrate it. We did the mechanism of that long ago. Test 2, you know it. You react nitric acid with sulfuric acid to form the NO2 plus ion, the aromatic ring ataxid, electrophilic aromatic substitution. But we can reduce that nitrobenzene to aniline with either hydrogen, platinum, or one of the metals there, iron, zinc, tin or tin chloride, and acidic water, and we end up getting the aniline out of it. The milder reducing group is the better. So if we had the tin chloride and acid, we can reduce the nitro completely without touching a carbonyl group with the tin chloride and acid. Okay. Or if we want to reduce just one nitro group, and we're careful about the amount of reagents we use, we can use ammonia, hydrogen sulfide, and ethanol, and we can just reduce one of the nitro groups. So the way to prepare amines via substitution reactions, we can add ammonia to methyl iodide, do an SN2 to kick out the iodide, and then more ammonia can come in and grab the extra hydrogen, so we form the methylamine. Okay, we can do this on bigger things, but it isn't one of the better ways to make a primary amine, okay, or an amine in general. There are much better ways to do it, so it's best if you don't do this on the test. Okay, because we end up with the chance of over-alkylating it. So we could get a mix of the monoalkylated, the dialkylated, the trialkylated, and the tetraalkylated compounds, all if we started with ammonia. So we can get a big mess out of it depending on what we have. So instead of this, it would be much better to do it in a way that we can form an amine in high yield purely. So we can add azide. We've talked about it in the past. It's a great nucleophile. It can displace a primary bromide to make the benzyl azide here, and the benzyl azide we can reduce with hydrogen and platinum or LAH to the primary amine. Now in this, we did not change the number of carbons in the molecule. All we did was add the nitrogen on to the number of carbons we had already. Another way we can do it is the Gabriel synthesis, where we use the potassium phthalimide or make potassium phthalimide by adding KOH to the phthalimide. We remove the hydrogen to make the anion, and that nitrogen is a great nucleophile, so we can do an SN2 displacement on any primary halide to form the alkylated phthalimide. And then from here, we can cleave out the nitrogen in a couple of ways. We can do it with either acidic water, where we get the protonated benzylamine and the orthophthalic acid, or we can add hydrazine that gives us this, where we've taken the nitrogen out of it and we get the benzylamine. So there, either way is okay. Health-wise, it's probably better to do the top way with just acidic water than working with hydrazine, because hydrazine is an easy thing to work with. So preparation of amines by a reductive amination. In a reductive amination, two things are going on. We are taking a ketone and reducing it from 2 bonds to a more electronegative atom on that carbon to, in the end, just having 1 bond on it. So we are making an amine, that's the amination portion of it, and we are reducing the carbon from having 2 bonds to a more electronegative atom to 1. Hence the reductive amination. So it goes through the imine, and then the imine we can reduce down to the amine as we go along. And this process can be used to form the following amines. We can make a primary amine where we use ammonia as our nitrogen source. We can make a secondary amine where we use a primary amine as our nucleophile, or we can make a tertiary amine where we would use a secondary amine as our nucleophile. We can't use a tertiary amine in this to make anything, because the tertiary amine doesn't have, if it added to something, it'd have a positive charge on it. We can never get that back to neutral. So we can do these 3 ways to make a amine. So the Gabriel synthesis is we add hydroxide to phthalimide, then we add whatever alkyl halide we need, followed by either acidic water or hydrazine, and this gives us our, in this example, our butanamine. Okay. The azide synthesis, we would start with the same 1-bromobutane. We'd add azide to it, and then after that we could add our LH to that, and that reduces it down to butanamine, 1-butanamine. Or the reductive amination, if we wanted to make this, we could start with an aldehyde. We could add ammonia and our reducing agent, sodium borohydride. We need a weak reducing agent, and that would give us the 1-butanamine. So those are the ways we can make an amine easily in good yield. Okay, the top 2 only make primary amines. Doesn't work with any others. Right? But the bottom one, you can make a primary, you can make a secondary, you can make a tertiary amine with it. So we can do this type of reaction many different ways, starting with different carbonyls. We can start with acetophenone. We can make a primary amine. We could add acetaldehyde to that, and we could make a secondary amine from that. Or we could start with acetaldehyde and reduce it to the ethylamine, and then add acetophenone and reduce that. There's more than one way to make any one of these reactions that we'll talk about throughout this semester.